Okay, so at the end of last class, what we were doing was the ether cleavage. So the intermediate, as we had just seen there. Let's make this a little bit better. So what we will do is an analysis of our ether. So look on each side and determine what are the, is this a primary, secondary, the type of carbon. So if you've got a primary, this is going to go SN2. And if on your molecule you've got a HBr, if you've got a tertiary carbon like this one, tertiary, it is going to undergo an SN1. So those are really the two options. So primary carbon will undergo an SN2, tertiary will undergo an SN1. And so the first step in each case is exactly the same. You protonate your ether. This will generate the leaving group, which is going to leave. So in this case, because we've got a tertiary, we're going to do an SN1 reaction. So this can leave. And we've got our isopropanol, or sorry, sec-butanol plus our carbocation. And then the bromide will come in and grab that, attack that. This will give us our two products. And as I said, I won't do an example where it's two secondary carbons. That wouldn't make any sense for a number of reasons. So those are really the two options that we'll see. Do you have do an analysis on each side for each carbon, which makes up the ether, and then if you find a tertiary one, the mechanism will be an SN1 reaction. If you find a primary one or a methyl, then it will be an SN2 reaction. So those are basically the two ways that this would work. But yeah, you really have to use a strong acid and you have to heat it up to get this to work. Because ethers, as we've seen before, are they're the solvents that we use, and we use them with really basic molecules, and they don't react. So they're really susceptible to strong acids and high temperatures. So that's the last little bit on ether cleavage. So the chapter on ethers is actually quite short because they're not reactive. There is one reaction that we need to talk about though, which is basically an introduction into the next section of the course. And that is the Claisen rearrangement. Okay, let's see here. And this reaction works with or sorry, allyl. Okay, so the aryl group here is the ring, right? That's an old term for aryl, is just an aromatic ring was aryl. The allyl part is in pink. Remember, we had seen allyl groups before. So allyl. And vinyl is a short term for the this part here. So these are the two situations where this reaction works. And this is what we would call a pericyclic reaction. So long time ago, we described what this was when we were doing different types of reactions. So this would have been way back in Organic 1. So these are concerted reactions where all the bonds are being formed and they're concerted. So all the bonds are forming and breaking at the same time. The other thing which is common about pericyclic reactions is that they often involve the conversion of pi bonds into sigma bonds. So you're making stronger bonds. So pi bonds are being converted into sigma bonds. Remember, pi bonds, sideways overlap of electrons, the pi bonds, sideways overlap of electrons, sigma bonds, head-to-head overlap. So they're technically stronger bonds. And the way that this would work, and we'll do it with the vinyl allyl ether first, is that we have a transition state where it's a cyclic transition state and all the electrons basically move around in a ring. So these electrons are going to go here to make a sigma bond. So these make a sigma bond. These electrons are going to move here. This is going to make a pi bond. And these electrons are going to move here. And this is going to, it's going to break a sigma bond and make a pi bond. So the yellow arrow makes and breaks a pi bond. the red arrow breaks a pi bond to make a sigma bond, and the green arrow breaks a sigma bond to make a pi bond. And so what we end up with is this. And if you do the energies of all of the various bonds, the final product is thermodynamically the more stable. So that's one of the driving forces for it. So all three of these the movements of these electrons, it's basically, it's a grand total of 6 electrons, and it's in a cycle. So we are going to see a bit later on in the course, when you've got 6 electrons in a circle, it's going to be one of the characteristics of aromaticity, which is stability. And so it's very similar to that, except for it's there's a slight nuance difference to it all. But anyway, it's the movement of six electrons in this transition state. So we're moving 6 electrons. Now, the aromatic one is probably the more popular of the two, because there's an added twist to it, which makes it the reaction even more powerful. So let's do that. Okay, so now let's do this. So remember, aromatic rings, if you're ever doing this, and your aromatic ring is drawn like the one on the left-hand side here, and you need your double bond, you just move it over because there's a resonance structure where it can move over, right? So these electrons go here, these electrons go here, these electrons go here, and that's your resonance structure that will get you to the place where you want to be, because you need this bond here. Now, it doesn't matter where you start, because you're going to get the same answer. But I'm going to start with this yellow arrow and attack the end. And so that carbon has got 4 bonds. We need to move over these pi electrons. We're going to move those to there. Now, this carbon here has got too many bonds, so we're going to break that last bond and move these electrons here. So what does that give us? That gives us the following. That gives us this. So if I label the carbons here, A, B, C, A, B, C. Now there's something else which is really important, and I'm going to draw this little proton on here like this. It doesn't stay in this form very long at all. It quickly transforms into this. Actually, this quickly transforms into this. And this process here on this arrow in red, this is tautomerization, which I'm spelling wrong here. And this is the one example, if you think back to our when we were doing our A, C. When we're doing the hydroboration reaction on a triple bond, and this quickly tautomerized to the keto form. 1, 2, 3, 4, yeah, A, B, C, D. Basically, I said every time you've got a ketone or an aldehyde, for every 100,000 molecules of ketone, there's the enol form of one in the bottle. You know, it's just a natural equilibrium between the two, but it heavily favors the carbonyl as opposed to the enol. This is the one example where it's exactly the opposite. So this, you could think of this as the keto form, and this is the enol form. And the reason why it favors the enol in this case is because of the aromatic ring. So the next section of the course, we're going to be talking about stability of aromatic rings. And by enolizing to form the enol, you regain the aromaticity. So this is the example where the enol is the favored form. So this is just a tautomerization. So the really wonderful thing about this Claisen rearrangement is you just take your molecule, put it in a flask, heat it up, and it does the Claisen rearrangement, and then it tautomerizes, and you've effectively put this allyl group on made this carbon-carbon bond between where this little yellow arrow is here. So you're making a carbon-carbon bond between here and here. Anytime, remember, organic chemists, that's what they want to do, make carbon-carbon bonds. So this is really, it's quite a neat little reaction. So it's 6 electrons moving around in a ring across 6 atoms, and all of you can move all of the arrows at the same time. So the next question might be, how do you make these allyl aryl ethers? And the most common way to do this is just exactly what we did before, the Williamson synthesis. So you take your phenol, you react it with, say, sodium hydride. Yep. This will give you your, so deprotonate it. Then you can throw in your allyl bromide. This will be an SN2 reaction. And voila, you have your allyl ether. And then this is basically ready to go for your Claisen rearrangement. So remember, when we're drawing this, I would redraw this product so that, like, I'd rotate this little bond here so everything was lined up properly. But these are the same molecules. It's just drawn with the bond rotated. And then this is ready to go. And so depending upon where the substitution patterns on your, like let's, like depending upon the substitution pattern on this double bond here, you can make some really interesting, like this double bond. Like here I've just drawn it, there's one substituent here, but you could have other ones in other positions. So, and that's gonna, like, for example, if we had, let's just put another methyl group here for the sake of argument. Then when we do this reaction, heat it up, these electrons go there, those electrons go there, these electrons go there. I'll draw the keto form first. So A, B, C. And I'll call this D. A, B, C, D. And this would quickly enolize, tautomerize to the corresponding phenol. Then there's all sorts of wonderful things you could do with this compound here. So remember, it's this little proton here, which I hadn't drawn, which ends up, this proton ends up here. And if, yeah, there's been all sorts of interesting, this is just a, pericyclic reactions are really, the pericyclic reaction we'll talk about next is the Diels-Alder reaction, which you guys did in the lab. And we'll do that after the midterm, which is coming up. So yeah, we won't get to that before the midterm, I don't think. Anyway, let's maybe do an example, another example here. Heat. Sometimes the symbol for heat is just a little triangle. And we've got an extra carbon here. Right. So as I said before, you can, it doesn't really matter where you start out, but I always like to start where you're making your two bonds. So between here and here. So these electrons go there. And then once we go there, then we have to move those other pi electrons because that carbon's going to have too many electrons. Then you can move those ones there. And then last but not least, we're going to break that last bond. I'll put this one in blue. So this one goes around to here. So in the end, every carbon it's got the appropriate number of electrons in it. And so our intermediate is going to be this. And then this is going to enolize. To make the phenol. And now we've actually got a, so we've got a carbon on this methyl group here. Yeah, sometimes when you go from a ketone, say to the enol, this is a tautomerization, but sometimes if you're going in this specifically in this direction, people call it an enolization because you're making the enol. So that's why I wrote enolize there. Yeah, and that's basically it. I don't know what else to say about the Claisen, but that was the last part. Was for the ether section was this Claisen rearrangement. It's quite a neat reaction. So it's 9:30 now. I figured that on Thursday, unless there's an immediate question, Thursday. Is there any questions about this? Okay, well, I'll take that as a no. I figured on Thursday what we would do all Thursday is a review for the midterm. So the midterm's next Tuesday. I think so. Yeah, it's the second midterm. So on Moodle, I basically opened up an old midterm from last year. You'll notice that when you look at it, um, we're a bit behind where last year's class was. So there's a question on the Diels-Alder, which obviously we haven't covered yet, so don't worry about that. And there's a question on conjugated systems, which you might be able to answer the question too, because the mechanism we've seen before, it's just reinforcing something before, but we're slightly behind where the last year's class was. So take a look at the test and see what you think of it. The format last year, we hadn't sort of entered the pandemic, so it was basically a paper and pencil type of exam. So what I figured we would do for this midterm was, I don't know if the problem with the last one was a top hat problem or a proctorial problem, because when you make tests on top hat, I don't know if the issue actually was a top hat issue or was the software for proctorial was causing problems with it. So what I thought we would do this time is we would just do a top hat test, but rather than doing proctorial recording everything, we would just use Zoom, and that might uncomplicate things a bit. So what we'll do is and I think that, so we'll just have to have Zoom on and turn on your camera and that sort of stuff. But if you're doing your test with like your main screen with just the top hat test, you shouldn't be distracted by the rest of the Zoom stuff. And that way, if you've got a question, you can just message me a little question on your through the messenger. So that's probably what we'll do. I'll set up a practice sort of test again, and we'll see if it works. I'll do that sometime this week. So that's what we'll do. Now the next question is dealing with how to study for this sort of stuff. So it seems as though like there's lots of fun things that you could actually, like when it comes to organic chemistry, it's kind of easy to make questions for yourself. And so yeah, I'll make it. There's a question about an oxidation assignment and an ether assignment. I'll put a short one together and I'll start it. It'll be due after the midterm, but you can at least look at it. And so you get an idea of some of the questions for it. It won't be particularly long. But yeah, I'll make a little assignment for oxidations. Actually, it's not really oxidations. It's a chapter on alcohols and ethers. So remember, alcohols, there was a big part of it was reductions. The other part was oxidations. Now this is what I was going to say. So I don't know if people have because this year has been pretty chaotic and everyone's off in their own little area of the world. there is a way to basically, if you need somebody to study with, maybe we can sort of set up a system of people to study with, because you can basically quiz each other on organic chemistry, or even test one another. Now, there is a there's a game you could play with your friends, an organic chemistry game. And basically it goes like this. So you could put any molecule you want. You can start off wherever. So I'll start off with this alcohol. So it's almost like cards. I am going to play this alcohol, the secondary alcohol here. And what are you going to do with it? So the next person could say, well, I'm going to react this with PCC and dichloromethane. And I'm going to make this. Now it's your turn. And so if what they draw is actually wrong, then that would be the end of, you would correct it, right? But what are you going to then do with this? And I would call, so what reaction do we want to do with this ketone here? You could say something like, well, I'm going to react this with this Grignard reagent, and it's going to make I'll draw out the whole thing. This. Then what are we going to do? So you basically, I would call this chemistry snafu, right? So whoever your opponent is, they can't really oxidize that alcohol, can they? Because it's a tertiary alcohol. So none of the oxidation reactions are going to work. And you have to get out of this sort of jam by doing something else. So what you could do is you could react this with, say, let's see here. We can make a sulfonate with this. And I think you could use triethylamine, something like that. And then you've got your sulfonate. All right, so what's the next person gonna do? Well, I know that this is a leaving group, so I'm gonna use a base and I'm gonna eliminate this. And so this will eliminate this. And there's basically, it doesn't matter which carbon it would be, this one or this one, there it's exactly the same thing, it would be that. And what's the next reaction we're gonna do? And so now you've made an alkene, and then there's a whole bunch of possibilities here, right? So the fun thing about this game, and of course it is fun, is that if you've got all of your little reaction your reaction webs built for all of the various functional groups, you can keep on playing this until you come to a dead end, like there's no reactions left to do, or the molecule you've made is so complex there's no other possible reaction you could do with it. And you can modify the game as well as saying that you can't go back on yourself. Like, for example, if in the very first step you made this, if you could say that one of the rules is you can't make what we've already made before. So this would effectively block off going this direction to make a, like using, say, sodium borohydride. If you played with the rules that you can't go backwards. But but you don't need to play, you could go backwards and then do something else, right? It all depends on how you want to play it. But once you've got to this double bond, now you've got all of the double bond reactions to do. So you could say something like, well, I'm going to use borohydride, H2O, and sodium hydroxide, and this is going to make this alcohol here, and you've introduced some, this would now be up. Then what are you going to do? Well, now you can do a Jones reagent, right? Let's do Jones. You've already used PCC, so you can't use that. And now you've got this. So there's all sorts of fun things you could do, right? So it's it's a nice little way of practicing organic chemistry, at least the various reactions for it. And it's a good way of checking to see if what you've made is actually, particularly if you're doing it with a group of 3 people or something like that, you can all check each other's work to see if that reaction is what's going on. Does that make sense? I guess I could write out the rules officially, but this is what I would do if I wanted to play my organic chemistry game. Which leads me to the next point. So, what I was going to suggest was that everyone should think of a question and send it to me and say, I want this question on the midterm. And if you come up with this is the question, this is the answer, and here are some good wrong answers for it, that would be awesome, because then what we could do is we could effectively compose an exam which is based upon questions that you come up with. And it's a good way of actually studying for a test. So, so if you want to come up with a question which you think is good, and if it's something which I don't think is good, then I won't, of course, include it. But it's a good way to actually help study for an exam, making up questions. Because really all we're doing is drawing. Yeah, so it's, yeah, creativity is always fun, right? And that's the reason why. And so this whole little scheme of drawing all these little reactions, this little organic chemistry snafu game, it's the fun part of organic chemistry. It's just making stuff out of other stuff and seeing where we can get with it, right? So just blindly adding things to this has already led me to this from here. And that's actually pretty cool, right? And then the other fun thing is later on in the class, we're going to learn how to do all the chemistry of aromatic rings, right? And so there's a whole bunch of chemistry there that we can do. And we haven't even finished all of the fun stuff to do with carbonyls, right? So this could be reduced. We've already used a Grignard reagent on it, so that's sort of stopped that. We can't do the Grignard reagent, so I guess we'd have to reduce it. And that would actually probably win the game because we've already done both of the oxidations. But yeah, we've already done that other oxidation. So if you were to reduce this with, say, lithium aluminum hydride, we would end up with this. Oh, it wouldn't win the game because there's other things you could do. We've already made alcohol into a like into a sulfonate. But we could do something like this. And to convert that into an ether, now what are you going to do, right? Cleave the ether, I guess that'd be going backwards, right? So you'd basically trap them and you'd win. All sorts of neat stuff. So on Thursday, what we'll do is basically a review of all of the reactions that we're going to cover in the test. The exam will focus on things that we've covered since the last midterm, but of course, everything is in some level cumulative because we're always building upon what we've done before. So we'll keep that in mind, but maybe what we'll do is I would, in the meantime, I would, for each functional group we've covered so far, like alcohols, I would make my reaction web of how to do different things with it, whether it's an oxidation or converting it into an ether or converting it into a leaving group. Remember, we could do SN2 type reactions with the phosphorus tribromide and the thionyl chloride. There's ways to make it into alkyl halides. So I would make my reaction webs with all of the functional groups that we've seen so far. And that once doing that, that helps with coming up with little routes and stuff to. But we'll do a review on Thursday. And if you have any questions, ask. There will be some synthesis type questions, yes, because those are the fun ones. Yes. But yeah, so on Thursday, come with questions. If you want to propose a question for the test, propose that. And make reaction webs for each thing we've done so far, like basically the tools in our toolbox. And then on Thursday, we'll try to have a review of what we've done. I'll ask a whole bunch of, I could ask a bunch of top hat questions, that sort of stuff. And we'll go from there. Does that sound good? I'll take that as, yes, that sounds awesome. Okay. Okay. All right. So I think that's basically, yeah, I think we're basically, our time is essentially over. So yeah, I guess I'll see everybody on Thursday. And if you have any questions, let me know. And we'll try to play some organic chemistry games in the future. All right. Have a good day, everybody. Stay warm, stay safe in the snow and all that sort of stuff. All right. And this.